Hello, my name is James Park, and this is my lab for magnetic field of a bar magnet. Alright, so the purpose was to observe the relationship between distance and the magnetic field, and to visualize magnetic fields, and to measure dependencies of distance of small bar magnets. Sorry, and the results were that the n is equal to negative 2.9, and the magnetic dipole moment is equal to 3.49. Alright. Now the physical constants or the physics constants that we have to know was the distance dependent equation, which is b bar is equal to krn, and then ln of bx is equal to ln of k plus n to the ln of r, and then the Bevel-Savart law, which is equal to the constant times 1 over r cubed times 3 times the dipole moment, the magnetic dipole moment, times r hat again, minus the dipole moment. Alright. The procedure. So the procedure was to download three apps, or one or three apps. Our group decided to choose the Tesla meter app, and to locate the chip on the phone, the magnetometer chip, and to line up the phone to compensate the magnetic north, where the x component is equal to 0, and to measure the distance where the magnetic field was equal to multiple given values and record those values. Alright, so the data we got, we see the distances, then we see all the recorded values, and then we can see that the slope that the recorded values make is equal to this, where this slope, negative 2.9, is equal to the n, and negative 14.175 is equal to the ln of b, which we can talk more about later on. Alright, so the observations was that as distance between the magnetometer and the magnet got smaller, the magnetic field of x component increases, and when the meter is far enough from the magnet, the x component is 0. Alright, so the calculations were that since ln of bx is equal to ln of k plus n ln of r, and we know what n is, and we know what bx is, and r is just 1, we can just substitute that in, and then we can get the answer for k, which we got was equal to 6.98 times 10 to the negative 7. Same thing for this case where b bar is equal to k r over n, and we know that k r over n is equal to the constant times the 2 magnetic dipole divided by r cubed. And so when you just do the algebra and solve for the magnetic dipole, we get that the constant times k r to 2 n plus 3 divided by 2 is equal to the moment. Therefore, the moment is equal to 3.49 a times m squared. Alright, now the computational model. So in the computation model, we just stated the universal constant, the magnitude we found earlier, the dipole magnitude. And here we're just putting in the B equation there so we can just figure out the magnetic dipole. And then there's code later on that I haven't included in this slide that just helps us visualize this visualization right here, where we see that this is on axis and this is the magnet, and these are all the ones perpendicular, and this is the 45 degrees, and we can see that the B at 45 degrees at distance is equal to 1.424 e to the negative 5 and 4.273 negative 5, which is relatively similar to the observed model. Alright, so the potential errors and assumptions that we have to make were, so the assumptions were that the bar magnet acts as a magnetic dipole and the magnetic field falls off as distance increases. And the potential errors, or like where the errors could have came from, was there could have been a lot of other outside forces, such as other electronics like our phones, or like magnetic objects, just like maybe computers or such, that could have skewed our observed data. And the exact location of the magnetometer in the phone might have not been found correctly due to human error, which might have caused the difference between observation and the computational. So the observational questions. So which of these systems statements described are true? Well, so when the magnetometer is far away from the magnet, it measures a near zero magnetic field. This is true. And then as magnetometer was closer to the magnet, the measured x component of the magnetic field increases. Okay, these two are the only true ones, and every other one is not true. Alright, so the discussion: if you hadn't oriented your experimental composite for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, how would your results have changed? So the Earth's magnetic field would have had an effect on the magnet's magnetic field, therefore it would have skewed the results. And if you were to stick two identical magnets together end to end and run the experiment again, how would you expect your measurements to differ? Well, since you're just sticking two together, you're just doubling the magnetic field. However, it's not going to change the direction. So the magnetic field's magnitude will double, but the direction will stay the same. Alright, that was my lab. Thank you.